Many people have the impression that mathematicians sit in the ivory tower and churn out equations that no one seems to understand or even care about. Well, indeed, there are many mathematical problems which are too deep for the non-expert to understand. There are also many mathematicians working on interesting, practical, challenging problems which impact our daily lives. So my colleagues in mathematical sciences at NTU will now tell you more about the kind of work they do.
Optimization allows us to make the best use of limited resources, or to find the best strategy from limited information. I work on the mathematics of optimization. My research focuses on the properties of convex optimization models and the design and analysis of algorithms to solve them. One of my research projects studies a new algorithm for nuclear norm-minimization models. Such models are used in designing recommender systems. When the large stores, such as Amazon, sell products to customers, they often rely on the recommender system to suggest more products that a customer is likely to be interested in. The recommender system may draw on data from past sales to other customers, and a nuclear norm minimization model can help you find the best recommendation to a customer based on the customer's past purchase history.
Coding theory is part of the mathematics of communication. By communication, we mean physical communication between a transmitting and a receiving device. That could be two computers, say, connected via the internet. For wireless communication, it could be two devices with one or several antennas. You could think of your cell phone. While the devices themselves are the work of electrical engineers, coding theory helps in designing schemes that tell how to transmit data reliably, and a fair amount of math can be needed for that. Coding theory can also be found in data centers to protect from data loss.
In our field of mathematical logic, we touch on questions in philosophy, pure mathematics, and with applications to theoretical computer science and computational complexity. Why is this important? Well, because nowadays big data and computational science are fast emerging as key areas which are necessary to process large data sets and assist scientists in their scientific pursuits. It drives the frontier of physics, mathematics, computer science, and even biological science research.
Our research teams apply mathematical and statistical techniques to study various financial problems such as modeling and risk management, which are core business in banking and finance industry. Mathematically, we propose a robust control approach to construct portfolios. For example, we somehow want to improve the ordinary investment outcome to a more stabilized one. Statistically, we rely on the advanced big data science and AI techniques to improve our understanding of the financial market. Along this way, you can imagine the future of the industry, including banking and finance, will be automation with statistical data analysis.
So cryptography is basically the science that's trying to protect all the data you're using, for example, when you're connecting on the internet or when you're using your credit card. So we already have a lot of algorithms that can do cryptography, but we have more and more very tiny devices that have a limited computing power and limited memory. So the current cryptography cannot be used in these very small devices, and we have to develop new algorithm, new technology to afford this. So in NTU, we develop this kind of algorithm, and this is called the photon hash function that you can see here on the screen. And this hash function is actually extremely tiny and can fit in extremely tiny devices. And this hash function has been chosen as one of the worldwide standards.